the Pfaffian form would look like this: x plus 3 times dy minus y minus 2 times dx equals to 0. And if you wrote the differential equation in that form, it's technically a different differential equation. That one treats x and y symmetrically, and that one has no trouble with vertical lines. See, because what's the one I'm fussing over here? This vertical line through the point. What's the equation of that guy?
That's an undefined slope.
It has undefined slope, right? True enough. But what's its equation? This point is what? Minus 3, 2, right? This is the what? X equals minus 3. So intuitively speaking, if you look at x equals to minus 3, you have dx equals to 0. And look at this. Minus 3 plus 3 times dy minus parentheses y minus 2 times 0 equals to 0. So admittedly, guys, what I'm writing right here, for all intents and purposes at the moment, is formal nonsense. Okay? But this can be given a rigorous meaning. This can be given a rigorous meaning once you understand parametric equations. So I mention it to you now because it's part of the story. Right? But you can kind of save that for later in some sense. But anyway, I'd like you to see that really the proper understanding of this differential equation, you throw back in the vertical line and you've got all lines through the point. All right? Okay, so next order of business. Yes, sir.
Can you go back to the exceptional solution?
Yeah.
What is that?
That means there are certain solutions that when we do separation of variable, we're going to lose them. Because separation of variable it uses division. So if the thing we're dividing by is 0, that might be an exceptional solution. It's probably an exceptional solution. See, there was no exceptional solution here, example 3, because we never divided, right? In example 4, the exceptional solution would have been like, we never divided here, so we didn't run into that problem here. Like, I ended up multiplying the differentials. I never actually divided, yeah? So that's kind of why there was not that issue here. I think in my example 1, we also didn't really divide. So here, my point, what I'm trying to say here is, you might say, well, there's division, right? But there's no division that's introduced by the separation of variables. The division that was in this problem is already there from the start, you know? So like, in contrast here, there was no division by y minus 2 in the original differential equation, but by dividing, I made y equals to 2 a problem. That's the distinction, yeah.
So is that an explicit solution, or is that the exceptional solution?
This is the explicit general solution, in fact. Honest to goodness. Explicit general solution. Great question. Thank you. Yeah. Yep.
On example 5, do we need to have like C1, C2, C is just a general constant?
Oh no, we can just lump C1 and C2 into a constant, call it C.
Well, even when we're just like finding the parts of the problem to put together, we just always just have C instead of like C1.
Yeah, we can always just put, as long as we add a constant to either one of the integrations or the other, we'll be okay. But we do need to add a constant somewhere, and we do need to add a constant at that step. Like, we can't set the antiderivatives equal, solve for y, and then add a constant. That, to quote my community college professor, will not hunt. That dog will not hunt. So, and I say that because students do that. Let that not be a prophecy. Let that be a statement of the past. And I understand the thought process. The thought process goes something like, I'm in a hurry, I gotta get this done, I gotta get this done. At the very end of it, oh, I forgot to add a constant. I'll just add a constant. Unfortunately, you can't. You have to add the constant when you first did the integration here. Because the constant gets all intertwined with the algebra. Like here, see how the constant was added in the integration step, but through the algebra it ends up being multiplicative? That's interesting. So let's talk about orthogonal trajectories. So this is a nice application of like what we're doing right now. And we can find orthogonal trajectories just using the methods we have already, okay? So basically this is it. Given a curve, or family of curves, with dy dx equals to Pac-Man, you can find a family of orthogonal trajectories by solving what? Dy dx equals to what? What does it mean to be orthogonal? It means to be perpendicular, right? What does dy dx equal to Pac-Man say? It says that that family or that curve at a point, the slope is given by Pac-Man, right? So if you want the line which is perpendicular to the line with slope Pac-Man, what do you make the slope? If you want a line which is perpendicular to a line with slope 2, what slope do you want? Negative 1/2, right? So we do negative the reciprocal, so we just solve minus 1 over Pac-Man. And that'll get you the orthogonal trajectories for you. So example 7 here, we'll find the orthogonal trajectories to example 2. Excuse me, 2, did I say 2? I meant 6. Dummy. Me, not you. Okay, so dy dx equals to y minus 2 over x plus 3, right? So that's my original differential equation, right? I want to find orthogonal trajectories to that. What do? I flip the fraction and stick a minus in, which gives me dy dx equal to x plus 3 over, well, minus parentheses. Well, I guess I could just absorb the minus into the, I can write that 2 minus y. Is that okay with you guys? Let me just, my bad. I'll make up my mind here eventually, guys. I'm going to put a minus out front, and I'll leave that y minus 2. All right, fine. Now, how do we solve this thing? The only way we know how, right? Separate and integrate. So this gives me y minus 2 times dy equals to minus x plus 3 times dx. And so what is that? We integrate, what do we get? No natural logs. Nope, not this time. Easier than that, right? We get 1/2 y minus 2 quantity squared, right? Equals to minus 1/2 x plus 3 quantity squared plus a constant, which we can rewrite as x plus 3 squared plus y minus 2 squared equals to 2c. But we might as well call that r squared because that's what it is. We might as well call that constant r squared because it's the radius squared of the circle that we're looking at. Yeah? What's the circle? Circle where? Centered where? Yeah?
Why not just integrate with y minus 2 with respect to y instead of doing the new substitution of y minus 2?
Because this is better?
Is there a reason why it's better, or is it just better?
The question I'm asking right now. So what is that the equation of? That is a circle-centered where? Yeah. But you're right. We could have integrated them separately. And that's probably what I would have done as a student for sure. I just know where I'm headed at the moment, so I'm behaving as a physicist and assuming my answer, yes, yes. Fair enough. You're like, well, mathematically, wouldn't it be more natural to have like 1/2? I mean, we could go down that path if you integrate the, sort of, let us say, uninspired way. I mean, you can go down that path, but if you go down that path, what awaits you in terms of the analysis here, and I mean, more power to you if you want to, is, well, how do you say, then you would complete the square. If I did it right, that should be a minus. There's a minus 3x there, and that makes this a plus, and then you complete the square and you get to that. And well, if you do that, then the c is different too. But anyway, I think it's just, for this problem, you get it's just better to do it this way. But agreed, you might not do that. If you didn't do it that way, then you'd have more algebra to do. Fair enough. Granted, good question. But this is a circle centered at -3, 2, right, with radius r. And I would, in my defense, I have good reason to expect a circle centered at -3, 2 with radius r, because I go back to example 6, right? If we go back to example 6 and look at it, what do we have? What are the oh, you got it. Okay. What are the orthogonal trajectories here? What are they? I mean, intuitively, I think intuitively you could have answered this question without calculus, right? If I asked you what are the orthogonal trajectories to a family of lines that fan out from a single point, you should intuitively know, well, they're circles. Of course, they're circles, right? But calculus has derived that for us systematically. Those are the orthogonal trajectories. There are many applications of orthogonal trajectories. One of the most, yep.
You said orthogonal just means perpendicular, right?
Yeah, that means that they're orthogonal trajectories if wherever they intersect, the tangent line to the one curve and the tangent line to the other meet perpendicularly. So a good application of this would be, for example, like equipotential lines. In physics 2, you talk about equal voltage lines, right? The electric field lines are orthogonal trajectories to the equipotential lines. So the lines along which charge move are usually perpendicular to the lines along which the voltage are constant. So that's one of the reasons that orthogonal trajectories are interesting. And I just also think geometrically they're kind of cool. But anyway, tomorrow we will solve, we'll go over something called the integrating factor method. And that, paired with substitutions, that's pretty much our bag of tricks for this semester.